Welcome to this demonstration of Asterios, the ChronoSafe flagship software tool suite for the development of deterministic, safety-critical, real-time systems. First of all, let's consider today's situation briefly. Why do embedded electronics stakeholders need a game-changing development solution like Asterios? Three disruptive factors are actually growing at fast pace. Number one, software complexity with high safety and real-time constraints. Think, for instance, about autonomous driving, automated flight control, distance surgery, and so on. Second, certification, which is a very long and difficult process that needs to be accelerated to allow customers to meet business objectives. And third, to meet the high performance required by these software applications, multi-core and distributed hardware execution platforms are used. They create additional challenges, specifically related to software execution time. Altogether, these factors create an unsustainable gap between complexity and productivity levels for engineering teams. McKinsey has actually analyzed the specific situation of the automotive industry, which is facing these challenges too. They are definitely confirming this trend. No need to say that on top of productivity issues, we have to consider the safety risks themselves. Here are two prominent examples of catastrophic situations occurring as consequences for software task scheduling and execution that were not correctly designed. In 1969, with the Apollo 11 lunar landing system, and more recently with the MCAS system failure and certification issues of the Boeing 737 MAX. A lesson learnt from all of this is that time-accurate development platforms are now necessary that can guarantee both time determinism and safety and accelerate certification. This is actually the promise of the Asterios platform, which enforces determinism by construction. Asterios' main technology pillar is the LET, Logical Execution Time Development Paradigm. We will come back on this in the following slide. Asterios also provides a formalism through its SciC language that allows to seamlessly handle time specifications from design to code generation on target. It provides simulation and virtual prototyping capabilities independent of the hardware platform selected, as well as automatic code generation and certification kits to ease the certification process, eventually allowing incremental certification. The Asterios tool platform for the aerospace industry is a set of 4 software applications: Designer, Developer, RTK, and Checker. We will see them in action later. Let's focus on LET for a while. LET stands for Logical Execution Time. It is a novel and highly attractive software coding paradigm that enforces determinism, meaning reproducibility and predictability. It guarantees that for a given set of inputs, a given software function will always produce the same output, regardless of other functions executed. To understand what LET means for complex real-time software systems, think about a large orchestra, a symphony orchestra, for instance. In a symphony orchestra, you have the conductor, whose role is precisely to keep time and rhythms between all instruments, as well as for each instrument, synchronizing each and all of them to get the best performance together. Entering the world of software functions, the conductor, our Asterios LET paradigm, becomes the mastermind behind software task scheduling, respecting the predefined execution boundaries and data flow, resulting in a perfectly executed application, like a perfectly played symphony. Here we have the generic outline of the development processes most frequently used today. It shows the main steps and teams involved in system architecture development, with the trend towards model-based system engineering approaches, hardware and operating system development, application software development, test and validation, with activities ranging from software and software-hardware integration to functional system validation. Today, because validation and error detection are done late in the process, many interactions occur between these various teams, from downstream to upstream steps, calling for late modifications and delays, meaning growing development costs. Asterios is actually streamlining and automating the software development process, introducing an architecture dimension and safe by design paradigm to the software development process, removing many of the inefficient interactions that were shown before and rapidly achieving correct by design, on-target application execution, whatever the hardware target, single or multi-core. Let's now see Asterios in action on an example. Our use case is a flight control system, which here has been developed by a system team implementing a model-based development approach using ANSYS SCADE environments. Our target hardware platform is the iMX8 multi-core platform from NXP. The demonstration shows how, with Asterios, the SCS software application is developed with 3 roles in action: system designer, software architect, and software developer working together in 4 steps that we will detail in the demonstration. First step, system designer and software architect exchanging model information together. Second step, software architect optimizing the application architecture and scheduling. Third step, architect sending this optimized architecture to the software developers, who will on their side integrate everything, including the operating system and application code, on the selected hardware. Finally, fourth step, the on-target run validation. Let's see the demo. We can now start with the first step. System designer and software architect exchanging model information together using the Asterios Open API to model-based design environments. This shows the static architecture, which consists in a set of functions represented by blocks with inputs and outputs describing the data flow between functions. These different functions implement a flight control system application. Flight mode and flight controller functions implement control command algorithm. Alarm manager function is responsible for detecting abnormal altitude and speed. Plane function implements the physical model of the plane. And display logic implements the interface for inputs and outputs with external display test application. On top of this static architecture model, information on dynamics, including timing and partitioning constraints, can be added. Here, the blue boxes represent individual execution units, representing software tasks called agents, inside which is written their respective cycle time. This means that the function plane is implemented by the agent AG plane with a cycle rate requirement of 50 milliseconds. In other words, AG plane agent must be executed in 50 milliseconds. Then SCADA Architect generates two XML files in Open System Description (OSD) format, which describes the modules, their interdependencies, and the execution timing requirements. Let's now use Eclipse to look at the two OSD topology files previously generated thanks to the specific eOSD plugin. In the OAD file, we can see the list of the Asterios agents mapping the different functional blocks. In particular, we can see the one called AG plane has a behavior item reference 4, which is the ID of the functional block plane. Here is the full description in the OSAD file in the object called behavior item plane that has a reference ID 4, as expected, 3 functions, an init, a reset, and a plane flight control with its budget and cycle timing, some outputs, altitude and speed, some input, throttle command and elevator command. We can now run a script that will launch Asterios Designer. Designer will take the OSD files as input to automatically generate the size C code representing the formal description of the dynamic architecture of the flight control system. If we do a refresh, we can see the generated files and specifically the one that will allow us to call on Asterios developer for next steps. We can now go to the second step, Software Architect optimizing the application architecture and scheduling using Asterios Designer again, and more specifically its formal language size C and Asterios developer simulation capabilities. Now that we are running Asterios developer, we can see all the generated codes in detail and navigate. In particular, we can see that the Asterios agent AG plane contains the following information: the code corresponding to the communication glue code to get input values, the main cyclic function called plane flight control, the code corresponding to the communication glue code to set output values. We can now build the FCS application for a virtual platform, which is actually our Asterios simulator platform. If we execute the FCS in debug mode, we can see, with use of dedicated measurement tools, the time difference between synchronization points and check if they conform with the expected required value. When executing the FCS application, we can allow it to communicate with the display test application and then send altitude 1000 and speed 100 commands to the FCS application running on simulator. At this point, we can then see speeds and altitudes calculated by the FCS application on the display test application. We are now performing co-simulation with the same test environment as the one which will be used on final hardware later. At this stage, we are actually in the position to validate the correct application behavior very early in the development cycle, as well as start creating our final test scenarios. Now we are in the third step, Architect sending this optimized architecture to the software developers, who will on their side integrate everything, including operating system and application code on the selected hardware using Asterios Developer with its code generation capabilities and RTK kernel. In this step, we are going to proceed to the implementation phase of our flight control system on a real hardware platform. For this demo, we have selected a board named Asterios based on i.MX8 SoC to execute the FCS application on ARM Cortex-M4 core. Now let's build the FCS application to run on the i.MX8 Asterios board. Last but not least, the fourth step, the on-target run validation. We use the U-boot installed on i.MX8 board to download the executable via TFTP protocol and execute it. Let's reopen Display Test application and start the interaction with the flight control system, application running on i.MX8 hardware in the same way we did before with the simulator. The flight control system application running on the board is communicating with the display test application running on the PC through a physical Ethernet cable. Let's first set target speed to 100 and target altitude to 1000 as we did previously on the simulator. We can see that the FCS application is calculating plane speed and plane altitude with the same response curves as shown with the simulator. They are finalized with the same values on the display. This slide highlights an important step, which is not easy to show in such a demonstration, and which is the certification of the FCS application. With Asterios, customers can reach a DO178C DAL-A certification level faster. As shown here, the RTK used by Asterios is already certified by ChronoSafe DO178C DAL-A. While all files produced by Asterios Developer are checked and validated by Asterios Checker, which is qualified DO330TQL5. This is actually aligned with the certification strategy used by ChronoSafe for other industry safety standards, such as ISO 26262 for automotive, for instance. It's a no-brainer. Achieving certification is a challenge. To ensure success, ChronoSafe brings strong support to its customers at all stages of their project development and certification process. Another strong asset of the company being a team of 50 engineers, all experts in the development of safety-critical systems. In a nutshell, and to conclude, what you have seen in this demonstration is primarily what makes Asterios a unique solution on the market today. Its capability to streamline a right first-time development process with early guarantee of time and constraints and deterministic behavior, thanks to Asterios LET-based formalism. A front-to-back effective software integration process with upstream software architecture optimization, simulation, and code generation. A guaranteed temporal execution on complex architectures, here on a multi-core NXP platform, but we could have retargeted easily another hardware platform of same or greater complexity. The demonstration also highlights Asterios' openness to adapt to various system development environments. Eventually, with Asterios, customers gain reliability and performance, as well as a significant increase of their development process productivity. Thank you very much for your attention.